Hello everyone and welcome to my presentation. My name is Federico Sulis. I'm a PhD student of Paulista University in Brazil, and today I'm going to present my work. The title is Exploring the Waste Management Hierarchy Concept under eMergy Accounting Lens, the case of non-marketable food. Over the last few decades, due to environmental, social, and economic concerns, food waste has become an urgent issue. Therefore, to diminish food loss and waste is a crucial point to minimize production costs, improve food security and nutrition, and contribute towards environmental sustainability. To achieve this purpose, among several conceptual models proposed regarding waste management, the concept of the triangular hierarchy of waste management established by the European Commission has a key role. The environmental performance of anthropic systems needs an appropriate methods to be assessed. Among them, eMergy synthesis is receiving attention due to its donor-side perspective in quantifying real wealth. Several authors have evaluated the intermediate low levels of the food recovery hierarchy, calculating some indicators as the total eMergy, the invested and recovered eMergy, and the net eMergy. Common findings were high consumption of natural resources for landfilling, negative values of net eMergy for electricity production from landfill biogas, slightly positive values for composting process. All these authors have evaluated the same level of the hierarchy. Therefore, there is the necessity of a more holistic approach that we are going to consider in this work. Now, let's have a look to materials and methods. The object of these studies is the organic fraction generated by food supply centers. Food supply centers are concentrated wholesale markets for products, usually horticultural, where sellers and buyers directly perform market agreements. The food supply center object of these studies is called SEAGESP and is located in São Paulo state in Brazil. SEAGESP is the biggest food supply center of all Latin America. An average of 10,000 tons of horticultural products are traded each day. 150 tons of waste are generated each day. The organic fraction is 80%. In 2018, were sent to landfill 37,000 tons of organic fraction. 80% of this organic fraction is non-marketable food. Non-marketable food is food unattractive for consumers or too ripe for the sales time of buyers at retail level. But this food is still edible and with high nutritional value. Regarding the organic fraction management, we have evaluated three different scenarios. The first one is landfilling 100% of this organic fraction. The second one is landfilling 100% of this organic fraction with electricity production. The last one is recognizing the 80% of this organic fraction constituted by non-marketable food and donated it, while the residual 20% is sent to landfill with electricity production. Depending on the chosen option along the waste hierarchy, the eMergy used up during a waste treatment option sometimes results in eMergy benefits. According to eMergy rules, a waste treatment option can be represented as an interaction between the eMergy of waste with the eMergy invested in waste treatment. Their sum represents the total eMergy embodied on the assessed system, while eMR represents the eMergy recovered. It's easy to note that scenario 1, 2, and 3 represent different management levels of the food recovery hierarchy and that they have in common the same input. According to the most recent discussion in literature, including the concept of eMergy algebra, co-products and byproducts, basically the works of Agostinho, Brown, Gara, and Sant'Agata, we have considered in this work that eMergy of waste is lost. Therefore, the eMergy of organic fraction entering the scenario's boundaries is equal to 0. This is the approach named by Sant'Agata zero burden approach. Because the eMergy of waste is independent of the adopted option of the waste management, it's possible to affirm that recovered eMergy depends on invested eMergy and hypothesize that the eMergy used up to treat the waste behaves as an independent variable and the recovered eMergy as a dependent variable. Therefore, we can explore the recovered eMergy as a function of the invested eMergy along the food recovery hierarchy, where we can consider the same inputs, 1 ton of organic fraction, the invested eMergy as an independent variable, the recovered or saved eMergy as dependent variable, and through this mathematical model where y is a function of x, therefore the recovered eMergy is a function of the invested eMergy. Results and discussion. Here we have the energy diagram of the system under analysis, the IWACP Food Distribution Center. The marketable food arrives, is traded, and sold. The non-marketable food arrives, but in scenario 1 and 2 is treated as organic waste and sent to landfill. In scenario 3, the non-marketable food arrives as well, is recognized, is separated from the organic waste in 2 steps, and sent to charity institutions, while the residual fraction goes to landfill. This table shows the results regarding total eMergy use, invested, recovered, and net eMergy. It's clear that scenario 1 and scenario 2 have almost the same values of total eMergy use, while scenario 3 shows by far lower values. The same situation we have for the invested eMergy. The recovered eMergy of scenario 1 is 0 for definition, and for scenario 3 we have a difference of 2 magnitudes. Regarding the net eMergy is negative for scenario 1, for scenario 2, but is by far positive for scenario 3. Here we have the results of invested eMergy, recovered eMergy, and net eMergy for different percentages of non-marketable food sent to donation. It's clear that net eMergy remains positive until 11.5% of recovering rates. Higher the amounts of non-marketable food diverted to donation, higher will be the net eMergy, while the contribution of electricity generated by the residual fraction, obtained in case of substitution of scenario 1 with 2, is negligible. The eMergy contribution of the residual fraction sent to landfill on the total eMergy amount in scenario 3 is equivalent to 94%, indicating that even a slight improvement of non-marketable food donation rate could have a great impact on the reduction of resource consumption. This graph shows the recovered eMergy as dependent variable of the invested eMergy along the food recovery hierarchy. The graph includes the 3 scenarios evaluated in these studies, as well as other scenarios from literature. The scenarios distribution according to their recovered energy as a function of their respective invested energy seems to follow the triangular shape of the waste management concept, and it suggests a non-linear decreasing trend for the recovered energy along the hierarchical levels, from the highest to the lowest one. Highest priority levels, donation in this case, are able to recover several times more energy than its energy investments. The gray color dashed lines represents a hypothesis for these non-linear representations. This trend, if confirmed, could become a new way to support waste management options from a donor side perspective. Energy synthesis applied to different options for the management of non-marketable food from IWACP has shown higher net energy obtained by donation scenarios than landfilling. Donation is able to recover 29 times more energy than its energy investments. Under an energy perspective, the results emphasize that donation should be supported as the most appropriate waste management practice for the IWACP's non-marketable food. The analysis of the energy recovered as a function of the energy invested has depicted the existence of a non-linear decreasing trend allied with the concept of triangular hierarchy of waste management, from the highest to the lowest priority levels. Thank for your attention. I want to thank FAPESP Brazil for the scholarship and Paulista University. Bye!